Geometry Chapter 7, Lesson 3, and we want to look at applying similar triangles. Now that we know how we can prove that triangles are similar using AA, SAS, or SSS similarity, we want to then apply these to measuring things that are in the real world or things that we might want to measure that you can't necessarily go out and put a tape measure up against. Something like maybe a tree or a building or something like that. Now, similar triangles, I think, actually become a little bit more powerful than congruent triangles. You remember earlier in the year when we looked at congruent triangles, once we proved that two triangles were congruent, we could use CP/CTC then to say that the corresponding side that we didn't use is equal to another corresponding side. And that was good for figuring out lengths if the triangles are equal. The nice thing about similar triangles is the fact that that second triangle that is similar to the first, it doesn't matter the size. The size can be very large or very small. It doesn't matter because the sides remain proportional. The ratio of one figure to the other, can continue to be used to measure very large items if we just have very large triangles. So I think similar triangles is a little bit more powerful than maybe congruent triangles because proportionality is a much more useful thing. We can find a lot of things around us that might be proportional, but not necessarily a lot of things around us that are equal. So proportions become very important. So we want to remember what we've worked with in the previous lesson. And that is when we have a ratio, a similarity ratio, a ratio of one figure to the other, we begin with that similarity ratio, and then we can write other ratios that have a value that's missing, and then we can determine the missing value by using the property that the product of the extremes equals the product of the means. So just like in the previous lessons, we are going to want to start with that similarity ratio, and the nice thing about it is when we use SSS or SAS to prove triangles similar, the ratios that we have to use in order to prove the triangles similar is at the same time the similarity ratio as well. So we're actually figuring out two things at once if the figures happen to be similar. So I'm going to do two examples where we use similar triangles, and I want you to pay very close attention to the second example because there's something, a mathematical reminder that you need to be aware of when you go to do problems like that. So let's take a look at these two problems. Now in this first problem we have a satellite image of a storm, and let's say we want to know how far it is across this storm. So we can set up these triangles, and if these triangles are similar, then we can use a proportion, use the similarity ratio between the two to figure out the missing value. So I know that this angle here in this triangle and this one here in this triangle are equal because they are vertical. So then if I know that this side here, which is 140, and over its corresponding side, which reduces to 4 over 1, if that's the same ratio as this side over this corresponding side, which also reduces to 4 to 1, I know these two triangles are similar by the SAS similarity postulate or theorem. So because they're similar, I can use this similarity ratio, 4 to 1, to determine the length of our distance across this storm. So because I use this triangle in the numerator when I wrote these ratios, I want to use this value in the numerator, and then I can use this value in the denominator. I now have my proportion, and I simply apply the property that the products of the extremes, 4 times 150, is equal to the product of the means, x times 1 or x. So multiplying these together, I get x is 600. So this would be 600 unit distance. Okay, that's probably a mile, so 600 miles. Okay, so you can see by determining what the similarity ratio is, by proving the triangles similar, I have my similarity ratio to begin with. I can then write another ratio, set up my proportion, and determine the length. Okay, let's look at the second example, and again, there's something important I want you to notice. Now in this example, we have a person looking into a mirror that's looking at the height of this giraffe. Now why do we have a mirror? There's a scientific property that says the angle of incidence is equal to the angle of reflection, meaning that if you shine a light at a mirror at an angle, the angle that you shine the light into the mirror, when it reflects off, that angle is going to be exactly the same. So the angle of the light hitting the mirror is going to equal the angle of the light reflecting off the mirror. And you've done this intuitively when you've looked at a mirror. So you're standing in front of the mirror and someone is standing off to your side and you can't see them in the mirror when you're looking straight at it. However, if you move to the side so that your angle of view into the mirror is equal to the angle that they are standing looking in the mirror, you can then see them, because the light that's reflecting off of them into the mirror is now reflecting at the same angle, so you can see them. So this sets up very nicely for us when we want similar triangles, because if I let a mirror on the ground here and I place it in such a manner that I can just see the top of the giraffe, I know that this angle and this angle are the same, because this is the angle of incidence, the light hitting the mirror, and this is the angle of reflection, the light reflecting off. So these angles are equal. And because I'm measuring vertically with the ground, these lines are perpendicular, so I can have two right angles. So these triangles are similar by the AA similarity postulate. So because they're similar, I can use the ratio of the sides in order to determine the length. So the height of the giraffe would be my x over here. I want to know what that is. Now, you can't really see that. Let me see if I can... Okay, so I want to know what that is. Now, here's what I want you to notice. Notice that these measurement here is in 5 feet 3 inches, and these are in feet. When you're going to measure something, all of the units in your ratio have to be the same. Remember, if we want to find the ratio of one figure to the other, we have to change the units and then reduce. So as I look ahead, I'm either going to have to change these 2 feet measurements into inches, and then this feet measurement into inches, so everything's in inches, or I'm going to have to change this measurement, which is in feet and inches, into just feet. The choice is yours. Now, if you like to work with decimals, or you don't mind working with decimals, we can just leave this as feet. So I'm going to go ahead and do that. So I have 5 feet in the small triangle is in proportion to 15 feet in the large triangle, and if I reduce those, I have a ratio of 1 to 3. So then I have in the small triangle, because I did that on first, I need to put 5 feet 3 inches in my numerator to figure out the height of the giraffe. Now, 3 feet, or 3 inches, how many feet is that? Because again, it has to be in feet, because this ratio is in feet. So 3 inches out of 12 would give me the decimal equivalent of how many feet those are. So this reduces to 1/4. So this is 1/4 of a foot, and I know that 1/4 as a decimal is 0.25. So this person is 5.25 feet tall. So I can use that. And now the product of the extremes is equal to the product of the means. 3 times 5.25. Okay, and so then I can multiply this out. So 3 times 5 is 15, and 3 times 0.25 is 0.275. So the giraffe is 15.75 feet tall, or 15 3/4 feet tall. Now I'm going to convert this 3/4 or 0.75 back into inches. If 1/4 of a foot is 3 inches, then 3/4 of a foot would be 19 inches, so, or 9 inches, excuse me. So the giraffe is going to be 15 feet and 9 inches tall if I convert it back to that. So you have 15 feet 9 inches. So again, remember that we have to start with the similarity ratio. If you're dealing with different measurements, you're going to have to convert everything to the same measurement before you use it in order for your answer to come out the way you want it, and then you can convert it back into feet and inches or something, some other measurement if that's what you need to do at the end.